right this second. There is a sealed muscular chamber inside your chest generating enough explosive pressure to literally shoot liquid across a room.
Which is a pretty wild thing to think about.
Right, and in a tiny fraction of time, like exactly 0.8 seconds to be precise, something incredibly violent, highly coordinated, and utterly essential just happened inside you.
Yeah, and it happens, roughly 75 times a minute. Every single minute.
Every minute, keeping you upright, breathing, alive. So we are taking a deep dive today into the cardiac cycle, but I want to set the record straight right off the bat because most of us were taught a very comforting, very basic lie in high school biology.
Oh, absolutely. The old two-stroke pump myth.
Exactly. We were taught that the heart is basically just a simple pump. You know the drill. It squeezes, it releases. Systole, diastole, leb, dub.
Yeah, and I mean, it is comforting in its simplicity, absolutely. But that two-phase model radically oversimplifies what is actually a remarkably complex microscopic choreography.
Right.
If you want to really understand how you are alive right now, I want you to picture an old 20th century physiology lab.
Okay, I'm picturing it.
Think heavy brass instruments, ticking metronomes, miles of smoked chart paper spooling out across these big mahogany desks.
Wow, very vintage.
Yeah, that is where the real story of your heartbeat begins. We are going to look at the heartbeat not just as a muscle clenching, but as an incredibly precise, energy-dependent dance of fluid dynamics, pressure, and volume.
Which sounds intense.
It is. It is a dance that has taken the medical field well over a century to fully wrap its head around.
Okay, let's unpack this. Our mission for this deep dive is to slow down time. We are going to take that 0.8 seconds, stretch it out, and uncover the hidden mechanics of your survival beat by beat.
I love that.
And I promise you, by the time we are done today, the numbers on a pharmacy blood pressure cuff and that thumping you feel in your chest when you are lying in bed, they're going to make a whole lot more sense.
They really will.
But to understand the mechanics of those 0.8 seconds, we first need to understand how scientists even realized what was going on in there. Because for the longest time, we were essentially blind.
Totally blind.
We had to move from just listening to the outside of the heart to actually seeing its internal gears turning.
Right. And for the vast majority of medical history, listening was literally the only diagnostic tool we had.
Just a stethoscope.
Exactly. Before the 20th century, if a doctor wanted to know how your heart was functioning, they relied almost entirely on external acoustics. When René Laennec invented the stethoscope back in 1816, it was hailed as revolutionary.
Sure, it was a massive step up from just putting an ear to a chest.
Oh, massive. But it really only told half the story. A doctor could hear the lub-dub, but they couldn't quantify the invisible pressure changes causing those sounds. You couldn't measure the engine's horsepower while it was running, basically.
It sounds like a mechanic trying to diagnose a failing transmission just by listening to a car rattle down the highway.
That is exactly what it was like.
Like, sure, a really experienced mechanic might hear a clank and guess, oh, that is your third gear, but they can't actually see the gears grinding.
Right.
Today, they would just hook the car up to a diagnostic computer to see the real-time data.
Right.
But we were talking about the early 1900s here. There were no diagnostic computers, no ultrasound. So how on earth did anyone manage to look inside a beating, pressurized organ without modern tech? That sounds like a mechanical nightmare.
It was a massive physiological puzzle.
Yeah?
And the person who solved it was Carl J. Wiggers.
Oh, Wiggers.
Yep. In the 1910s to the 1930s, working at Western Reserve University, Wiggers decided that acoustic guesswork just, it simply wasn't enough. He wanted telemetry. He needed to measure invisible forces.
So what did he do?
Well, he meticulously designed and utilized delicate pressure transducers and optical manometers on animal hearts.
Okay.
He managed to simultaneously record the pressure in the left ventricle, the pressure in the aorta, the atrium, the volume of blood, the electrical signals, and the physical sounds.
Wait, all at the same time?
All at the same time. And here is the true stroke of genius. He plotted all of these distinct, complex measurements on a single piece of paper, sharing a single horizontal axis representing time.
Wait, so instead of looking at blood pressure on one chart and electrical signals on another, he just stacked them perfectly on top of each other.
Exactly.
He created a synchronized map of everything happening in the heart at the exact same millisecond.
What's fascinating here is that this exact chart, known today as the Wiggers diagram, it remains the single most reproduced figure in cardiovascular physiology TAD books worldwide.
Wow. After 100 years.
It hasn't fundamentally changed in a century. It completely revolutionized medicine because, for the very first time, bedside clinicians could connect the external sounds they heard through their stethoscopes to the invisible internal pressure changes of the heart.
They weren't just hearing a thump. They were seeing the physical forces that created the thump.
Precisely.
They could finally see the gears shifting. And it wasn't just Wiggers working on this, right?
Right, we should definitely briefly contextualize the intellectual atmosphere of that era. While Wiggers was mapping these synchronized phases, his contemporaries, Otto Frank and Ernest Starling, were independently discovering the underlying physics of the muscle itself.
Right, the Frank-Starling law.
Yes. They figured out how the physical stretch of the heart muscle directly relates to its contraction force.
So like pulling back a rubber band.
Exactly. The further you stretch it, the harder it snaps back. So you had this massive concurrent explosion of understanding regarding not just when the heart beats, but how it physically regulates its own power beat by beat.
So with Wiggers' diagnostic map in hand, let's actually zoom in. Let's take that 0.8-second cycle and walk through it, cause and effect.
Let's do it.
We are going to focus on the left side of the heart, which pumps blood to the whole body, just to keep things clear, though it is worth noting. The right side, which pumps to the lungs, is basically mirroring all of this at about 1/6 the pressure.
Right, much lower pressure on the right. But before we track a single drop of blood, we must establish the golden rule of the cardiac cycle.
Okay, what is the golden rule?
It all comes down to first principles in physics. Blood only moves from a chamber of higher pressure to a chamber of lower pressure. And it only moves through a valve that has been mechanically forced open by that exact pressure difference.
So it's forced?
Blood doesn't move because it wants to. It is violently pushed. Every single event we are about to discuss is an absolute slave to that one rule.
Higher pressure to lower pressure. Got it. So let's start at the top. The left atrium. Blood has just passively flowed in from the lungs. It is just sitting there. And then an electrical signal fires.
The electrical signal is the spark. If you have ever seen an ECG, an electrocardiogram, it is literally a map of the heart's electrical wiring.
Right, the little squiggly lines.
Yeah, and the very first little bump on that ECG line is called the P wave. That represents the electrical spark traveling through the tissue of the upper chamber, the atrium, telling those muscle fibers to contract.
And when they contract, the atrium squeezes.
Yes. And by this point, the atrium is already mostly full just from passive gravity and flow.
Right.
When it finally squeezes, it's just pushing that final 20 to 30% of blood down into the main pumping chamber, the ventricle.
Oh, it's just topping it off.
Exactly. In clinical terms, we call this the atrial kick. It is the final top-off before the main event.
And once that extra 30% of blood is forcefully shoved into the ventricle below, the pressure in that lower chamber abruptly spikes.
Right.
The inlet door, the mitral valve, it has no choice but to physically slam shut to prevent blood from flowing backward. Now we are in a completely sealed room. The ventricle gets its own electrical spark, and it starts to squeeze.
This is a critical moment.
The term in the sources for this is isovolumetric contraction. I want to clarify this term, isovolumetric, because it is crucial for understanding how violent this gets.
Go for it.
Think of it like taking a hard plastic water bottle that is totally full, capping it tightly, and then squeezing it with both hands. The pressure inside that bottle skyrockets. But because the cap is sealed, the volume of water inside doesn't change. No liquid escapes.
That is exactly what your ventricle is doing.
The pressure is climbing exponentially, but the blood has nowhere to go because the entrance valve and the exit valve, the aortic valve, are both shut tight.
The water bottle analogy is perfect. The ventricle is a sealed chamber contracting against a fixed, incompressible volume of liquid. And to build on that, think about the physical impact of that inlet valve slamming shut at the very beginning of this squeeze.
Oh, that makes a sound, right?
It does. That forceful physical impact is what creates the first heart sound, the lub of the lub-dub. You aren't hearing the muscle contract. You are literally hearing structural doors slamming shut to seal the chamber against immense pressure.
But the pressure is still climbing in this sealed bottle. It hits 80 millimeters of mercury. Something has to give. The pressure inside the ventricle finally overcomes the pressure in the massive artery waiting just outside the aorta,
which triggers the ejection. Following our golden rule, the aortic valve is violently forced open by the superior pressure. Blood is ejected out into the body, and the pressure in the ventricle continues to climb, peaking at roughly 120 millimeters of mercury.
Here's where it gets really interesting for you listening. That number, 120, is not random. That peak ejection pressure is quite literally the top number on your systolic blood pressure reading.
Yes.
When you get your blood pressure taken, that cuff isn't just giving you a generic health score. It is capturing the exact maximum physical force your left ventricle just achieved to blast blood through your arterial system.
It's a direct mechanical readout of that specific millisecond in the Wiggers diagram. And the moment that peak force is spent, the ejection ends.
So it drops.
The pressure in the relaxing ventricle suddenly plummets. But remember the golden rule, higher to lower pressure. Because the pressure in the aorta is now suddenly higher than the empty ventricle, the ejected blood tries to fall backward into the heart.
Which forcefully catches the flaps of the aortic valve and snaps them shut.
And that snapping shut is your second heart sound, the dub. So the lub is the inlet valves closing. The dub is the outlet valves closing.
Dub.
And what's wild to consider is that at a normal resting heart rate, those two sounds, the opening and closing of the exit doors, are separated by just 0.3 seconds.
Wow.
That is how blindingly fast the ejection phase happens.
For 0.3 seconds. And now the exit door is shut. The inlet door is still shut. We are back in an isovolumetric phase, a sealed chamber. But this time the ventricle is relaxing, not squeezing.
Right, it's letting go.
The pressure inside is in a total free fall, plummeting towards zero, but the volume of blood inside is staying exactly the same, which is practically zero, because it's a sealed, empty room.
And it continues to plummet until it finally drops below the pressure of the atrium waiting above it. Once that threshold is crossed, physics takes over. The mitral valve is forced open by the higher pressure above, and a new volume of blood rushes in to fill the empty ventricle.
Oh, and doesn't that make a sound sometimes too?
Yeah, actually. In some young people, or children, this rush of fluid is so rapid you can hear a third heart sound here in S3, which is the acoustic signature of blood crashing against the walls of the relaxing ventricle.
And then the cycle repeats. The electrical spark fires. The atrial tops it off. The chamber seals. It squeezes. It ejects. It relaxes. It fills. Over and over.
This raises an important question, though.
What's that?
Why do we need to slice a single heartbeat into all these microscopic, distinct phases? Why not just call it a beat?
I mean, that would be easier.
It would. Well, because these distinct mechanical phases dictate how we diagnose human disease. Take that ejection phase. Cardiologists measure exactly how much of the blood in the filled ventricle actually gets successfully pushed out. We call this the ejection fraction.
Ejection fraction, okay.
A normal ejection fraction is about 55 to 70%. The heart doesn't completely empty itself.
It always leaves a little in the tank.
Exactly. But if that number drops below 40%, we diagnose the patient with HFrEF heart failure with reduced ejection fraction. Their pump is failing to squeeze effectively.
So the rubber band is broken.
Yeah, and the cellular mechanism here is key. In HFrEF, the heart muscle walls have often become stretched out, thinned, and floppy, like an old rubber band that has lost its elastic recoil. It just can't generate the force.
Right.
This specific diagnosis, which dictates the daily medication and treatment for millions of people, is a direct numeric descendant of Wiggers' phase-by-phase framework.
But that brings up a really massive blind spot in medical history. Because Wiggers gave us this beautiful, nuanced model a century ago. It clearly shows the heart is doing many complex things across a single second. So why do so many people, and historically even a massive portion of the medical community, still think of the heart as just a simple squeeze and rest muscle? Where did this persistent two-stroke myth come from?
It comes from a deeply ingrained historical bias that we call the systolic paradigm.
Systolic paradigm.
For most of the 20th century, cardiology was utterly obsessed with the squeeze, systole. Because it's dramatic, it's mechanically intuitive, and as we just mentioned, it's very easy to measure with a metric like ejection fraction.
That makes sense.
The prevailing logic was, if a heart is failing, it must be because the pump is too weak to squeeze.
I'm going to push back on that, though, because honestly, that kind of makes intuitive sense.
It does.
Like when a muscle isn't flexing, it's resting. Isn't diastole the relaxation and filling phases? Isn't that just the heart taking a break? Doesn't the muscle just go limp and let gravity do the work of filling it back up?
I'm so glad you brought that up, because that is perhaps the single most dangerous misconception in the history of cardiology.
Wait, really?
Oh, absolutely. Diastole is absolutely not a passive resting state. It is a highly active, incredibly energy-consuming process. The medical term for this active relaxation is lusitropy. Look, the ventricular walls have to actively expend cellular energy, ATP, to uncouple their muscle fibers, forcefully relax, and essentially pull themselves open to create the vacuum-like pressure gradient that sucks blood in. It is an active mechanical pulling, not just a passive slumping.
Wow. So relaxing actually takes cellular work. If the heart runs out of energy, it can't
It
relax.
takes a tremendous amount of work,
Yeah.
and the dark side of misunderstanding this physiology is profound. Because of that systolic bias, for decades, patients who came to the doctor with all the terrifying symptoms of heart failure, severe shortness of breath, extreme fatigue, fluid backing up into their lungs, they were told their hearts were perfectly fine.
Seriously.
Why?
Because the doctor would measure their ejection fraction, their squeeze,
Yeah.
and it would come back completely normal.
So they just say, your pump is squeezing fine, your rubber band still has snaps, so you must be fine. And they were not fine. It wasn't until the 1980s and 1990s that undeniable clinical data forced medicine to recognize this massive blind spot. These patients, who were very frequently older women, by the way, whose symptoms were chronically dismissed as anxiety or just getting older, they didn't have a squeezing problem.
He had a relaxation problem.
Exactly. Their ventricular tissue had become incredibly thick and stiff. They squeezed beautifully, but imagine trying to fill a stiff leather pouch with water compared to a thin rubber balloon. The stiff leather resists filling.
Right.
They couldn't actively relax to fill properly during diastole. We now call this HFpEF heart failure with preserved ejection fraction. It makes up roughly half of all heart failure cases
By
today.
half.
And it was largely ignored for decades because we were trapped in a two-stroke mindset.
That is staggering. A diagnostic category that represents half of all heart failure just basically didn't exist a few decades ago because we weren't looking at the whole cycle. We forgot how to measure the relaxation. This really underscores why dissecting these phases matters. And it makes me think back to the Frank Starling law you mentioned earlier, the rubber band idea that more stretch equals more contraction force. Does that rule break down here too?
It absolutely breaks down.
Oh, wow.
The Frank Starling mechanism is a brilliant evolutionary adaptation in a healthy heart. If you are dehydrated and I give you rapid IV fluids, your heart fills with more volume, stretches further, and naturally bounces back with a stronger squeeze to pump that extra fluid out.
It auto-regulates.
Yes, it auto-regulates its own power. But in a failing heart, that curve flattens out. The tissue is either already stretched to its absolute limit, or it is too stiff to stretch at all. If you add more fluid to a failing heart, it doesn't give you more force. The fluid just hits a wall and backs up into the lungs.
That sounds really dangerous.
It is. That is exactly why fluid overload is so highly dangerous for heart failure patients. The built-in autoregulation is broken.
Okay, let's clear up a couple of other common misconceptions while we are myth-busting here, because when people picture a heart beating, they usually picture the entire organ clenching all at once, like a fist closing. But if that happened, it would violate the golden rule of pressure, wouldn't it?
Completely. If the whole heart squeezed at exactly the same time, the system would stall. The blood would have nowhere to go.
So how does it avoid that?
The electrical system of the heart prevents this. Specifically, there is a cluster of cells called the AV node that acts as a built-in traffic light. It engineers a deliberate 0.1 to 0.2 second delay between the upper atria squeezing and the lower ventricle squeezing.
Ah, so that is the deliberate delay that allows the atrial kick to top off the ventricle before the main event fires.
You got it.
The traffic light holds up the main contraction just long enough for the lower chamber to finish filling. That is incredible engineering.
Now, what about heart murmurs? I think the common fear is that a murmur means your heart muscle is actively failing or diseased.
Thankfully, no. Most murmurs have nothing to do with the muscle tissue itself. Really?
Yeah. A murmur is just the acoustic signature of turbulent fluid dynamics at a valve. If a valve is stiff and narrowed, like in aortic stenosis, you'll hear turbulence during the ejection phase as the blood forces its way through a very tight opening, like putting your thumb over a garden hose.
Oh, that makes sense.
If a valve is leaky, you'll hear turbulence when the valve is supposed to be sealed closed as blood trickles backward. It's a plumbing issue during a specific phase of the cycle, not necessarily a failing pump muscle.
So what does this all mean for you? Why should you care about atrial kicks and isovolumetric contraction as you go about your day?
Well, because Wigger's century-old phase mapping is literally interacting with you right now.
It really is.
If you were wearing a smartwatch and it has an atrial fibrillation detector, what it's actually doing is looking for the electrical signature of that atrial systole, that P wave we talked about.
If it senses that your upper chambers are quivering chaotically, instead of giving that coordinated electrical kick, it alerts you. The device on your wrist is quite literally diagnosing phase 1 of the cardiac cycle.
It's amazing technology.
And when you sit at the pharmacy and put your arm in that blood pressure cuff, you aren't just getting an arbitrary health score. You are capturing the exact peak and trough of a single left ventricular wave. Systolic is the explosive peak of the ejection phase. Diastolic is the lowest pressure point just before the next squeeze begins. It is the microscopic violence of the cardiac cycle rendered in 2 simple numbers.
If we connect this to the bigger picture, mastering these mechanics even explains peak human performance.
Like athletes.
Yes. If you look at an elite endurance athlete, they might have a resting heart rate of 40 beats per minute. That isn't because their heart is lazy. It's because their cardiac mechanics are so stunningly efficient. Their ventricles have such a massive stroke volume, they eject so much blood with a single powerful contraction that they simply require fewer beats per minute to achieve the exact same total cardiac output as you or me. Their phases are beautifully optimized, allowing for longer, more restorative diastolic filling times.
It is an absolute marvel of biological engineering. We've spent this entire time dissecting a mere 0.8 seconds of your life. But I want to leave you with one final provocative thought from the research to mull over. We talked extensively about how violent that ejection phase is.
That's really violent.
120 millimeters of mercury of pressure blasting a literal shockwave of blood out of the heart. Now consider the Windkessel effect.
Ah, the Windkessel effect, a true marvel of structural engineering.
Right. It's essentially a hydraulic shock absorber built into your chest. It's the way your elastic aorta takes that violent pulsatile shockwave from the ventricle and magically smooths it out. Because the aorta is packed with elastic fibers, it balloons outward to catch that 120 millimeter mercury fastball, absorbing the extreme kinetic energy.
And then during diastole.
As the heart relaxes, the aorta gently recoils, turning that explosive start and stop pulse into a continuous, steady river of blood for the rest of your body. Think about the incredible physical resilience required for your arteries to absorb that explosive isovolumetric shock wave 75 times a minute, every single minute for your entire life without shattering. It's unbelievable.
It really is the ultimate biological shock absorber, converting violent pulses into life-sustaining flow.
So next time you are sitting quietly and you feel that thump in your chest, I hope you listen to it a little differently. You aren't just hearing a simple 2-stroke pump. You're hearing structural doors slamming, invisible pressures peaking, and an active, energy-hungry relaxation that keeps you moving forward. Thanks for joining us on this deep dive.